does it always happen to me?
Come on, come here, boy. Come on. You freaky dog. I don't need to analyze. Every word that comes out is a lie. Make it look like it's so ice, ice. You won't make it to the finish line. Now if you gotta know the truth, we can't let you go. You was fine, never mind. Unpredictable. Fade out of the ground, you ain't no one. You was fine.
Hey there. Time for another Toolbox Tech Talk.
Sharing secrets, you wish really was part your life. Basic bullies, with no bullies. Does your wife know you're begging for my notice? Promise you're the same. Running for the magic. Show you like
Yeah, today's all about everything off grid, so something very close to my heart. Well, welcome back. Welcome back, everyone. So, God, holidays have slowed me down a little bit in terms of getting everything out in time. Sorry, I'm sending out my little notifications just a few minutes before going to air. But you can always just check out my channel at 1 o'clock on on a Sunday, and I should be there, so you don't have to wait for the email. But anyway, today is all about everything off-grid. Now, this is kind of something in my DNA. For those who don't know me, I've lived off-grid more than half my life. I initially in New South Wales in a rural property in the middle of the Wallamai National Park. It was pretty interesting introduction to off-grid living. So it was kind of, I like to describe myself as an accidental off-gridder. How can that be? Well, I don't know if anyone ever remembers, but around about 1991, there was this kind of crazy real estate market in Sydney where people were just buying stuff and, you got gazumped and it was awful. And if you saw a property you liked, you sort of had to just jump on it. You couldn't muck around. There was no second looks, really. And so me and my then partner bought an off-grid system, but we didn't know it was off-grid. We bought a property which kind of looked really lovely house out in the bush and the Wallamai, and I didn't really check out the power system. It had lights and things in the house, but unbeknownst to me, until we actually took possession, it actually ran off a diesel generator. God, how talk about due diligence. I think I'd probably spend more time thinking about buying a pair of shoes. But anyway, so we ended up at this house, and fun fact, it was actually owned by one of the Men at Work band members, Ron Strikett, the drummer from Men at Work. I believe they actually used to use it as their little hangout. So one of the rooms had keys and it said music room, and I thought, well, maybe this is where they wrote Vegemite sandwich. Anyway, I pretty quickly realised that running a diesel generator was a terrible idea. Really, just they were spending, because they kept a logbook, $250 a week. This is just a weekender for them on diesel to keep this place running. And so that was just unsustainable. So I reached back into my depth of knowledge because my background is in electronics, and I actually made my own inverter, got some old Telstra batteries. I got 3 75-watt Solar X panels, and I was away. I had my own off-grid system. The inverter promptly blew up because it was really not up for the job. And then I bought my first proper inverter, a Selectronic, or actually the name, and it's sitting behind me on the wall here, is called Inverter Power. That's what they branded them back then in 1991. And it was a 1 kilowatt modified square wave, nasty inverter, but it was a good inverter, but modified square wave is not the favourite thing. So Selectronic pretty quickly after that brought out actually they already had them out, but I hadn't purchased one, the SA21 sine wave, pure sine wave inverter. So I moved up to a quality inverter very quickly and stuck with it. So that did me very well for like 15 years that I lived there. So that's how I got into off-grid by accident, but I learned a lot from those early days, and started a business and started designing systems for other customers. And, here I am now telling you about everything off-grid. So I've got a bit of a presentation here. It's actually the introduction to a course that I run. So I will be running this course as 2 4-hour sessions, much longer than just a 1-hour intro like I'm doing today. But I'll email you that when the course is ready. But this is just a little taster of it. But it also introduces you some of the concepts about designing for off-grid. So without further ado, let me just get something up on screen here. Okay, and where am I? I'm over here. There we go. Right, so this course is based on the standard for designing a standalone power system, 4509 Part 2, which was published in 2010. Now, the reason I'm actually focusing on this is that we're in the process of rewriting 4509 Part 2. When I say we, the EL005 committee that I'm a member of, have been for like 12 years now. And we recently released the public comment draft, which you would have heard me talking about last week, for 4509 Part 1, which is the installation standard for standalone power systems. Part 2 is a bit more complicated. It's about design, so design principles. So I'm hoping that we might have a public comment draft out this year, because it is a a fairly major project rewrite to bring it up to current technologies, you could say. So, welcome everyone. I just saw a few people joined us. Please feel free to say in the chat where you're watching this from. I always love to know. We've got some of the regulars that usually turn up, but if there's any newbies, say hi. This session, by the way, is being recorded, and you'll probably see it pop up in my socials as well, serialized on LinkedIn or on Facebook. But for those that can't stay for the whole session, you can always just click on the link again any time, and you'll see the recording. So there you go. That's how it works. So everything off grid. Why do I call it everything off grid? Well, it's kind of like everything about off grid, not just the design principles, but also some of the considerations about living off grid. So let's get into it. And where's my mouse gone? Click on the wrong thing. I actually had a bit of a last minute hiccup when I couldn't get my stream started, but so far so good. Anyway, so let's talk about what is off grid like. Well, there's some very simple ways of living off grid, and I'm not shaming anyone who likes to live simply. I certainly started pretty simply with just 3 panels, but you know, if you've got a very small budget, you may have to think that living off grid is a bit like camping. And you know, you've got a very limited amount of storage and a very limited number of appliances that you can operate. And so, you know, if you don't mind living like a caveman, well, maybe not quite, but living like you're camping, you can get by with a very small system. But these days, it's become very, very achievable to have a really excellent off-grid system that does everything an on-grid system and more. When I say and more, for instance, no more blackouts. That's a big plus. And by the way, off-grid is not just for remote parts of Australia. People are actually going off-grid where there is power in the street. When I say going off-grid, it's more likely that it's a new build, a greenfield site. So where I live in the Yarra Valley, it's often a $30,000 fee just to connect to the grid. And so when you consider the ongoing cost of electricity thereafter, the total cost of ownership of a off-grid system is competitive with the grid over a 10-year period. So sometimes going off-grid is just choosing a more economically sensible solution. But it does come with a few caveats, and you've got to consider the limitations. So, that's kind of how I would put it. If you don't mind camping, you can have a very simple system, but if you want to spend a bit more, you can have basically a normal installation. So step 1 in this process, and let me just move my head out the way. Okay, there we go. Step 1 in this process is establishing your design criteria. And it's all about what are the loads and what are the energy resources, those two things. So when I say energy resources, where are you going to get your renewable energy from, or even your non-renewable energy? So, for instance, most people think of solar as the first choice, and that is by far the most popular because the sun is a very predictable resource. It does more or less come up every day. Even if it's overcast, it's still something. Whereas wind can be a very intermittent resource and very site-specific. Hydro, so micro-hydro, fantastic if you have the resource. So if you have a creek with a bit of a fall on it, like if you've got 10 metres or more, you can probably have more power than you know what to do with because the power of water is pretty amazing and the cost is actually very reasonable. But here in Australia, not so many sites are suitable. You need basically a good flow of water and a height difference between the inlet and the outlet. But it's in places like New Zealand, shout out to my Cuzzy bros, particularly in the South Island, I've seen a lot of microhydros. In fact, it's quite funny. Sometimes the complaint from the customer is we don't know what to do with all the power. Basically, our batteries are always full and we've got dump loads on just to keep the turbine under load. So it's a reverse problem sometimes. But coming back to what's most common, certainly here in Australia, is a solar battery system. Now, the other resource that you might want to consider is non-renewable. So, for instance, a backup system. I mean, it's great to have free energy from the sun and store it in your batteries, but sometimes, the weather's just not very good for a long period of time, and you start to fall on your requirements for a non-renewable resource, which is most likely going to be a generator. So diesel, petrol, or even gas. No, gas is really just a petrol engine with another type of manifold. So the other thing that's really important is doing an assessment of the electrical design and the demand of that. So that's about knowing what appliances you need to run. And this is really important because the difference between an off-grid system and an on-grid system is on-grid's kind of like you're not really capacity constrained more than the maximum rating of your circuit breaker, of your main switch. Whereas your off-grid, it's actually about your inverter rating and the amount of battery storage you have. So you've got to be a bit more precise about sizing a system to an energy demand. And that's what we're going to be looking at. So there's also what type of system do you want to build? How is it going to be configured? Now, there's a few terminologies here, which for those in the industry are probably very familiar with, and it's how does the system capture renewable energy and how does it store it? So an AC coupled system means that the generation source has an AC output and the storage system has an AC connection to it. And so they're coupled together through the AC network, i.e. Your submains between your solar inverter and your battery inverter, for instance. Whereas a DC coupled system is where the solar panels through a charge controller are directly connected to the batteries. Now, with the advent of hybrid systems, sometimes all of this is in one unit. You may well have an inverter, a MPPT, and a battery port all in one sort of piece of equipment called a hybrid inverter. So it's DC coupled internally, and they can even have AC coupled externally as well. So switched systems are not very common anymore. That's where you would actually choose to run from one source or another, such as a generator, or switch over to your inverter, kind of old school. I did start with a switched system because back then, with a 1 kilowatt inverter, I just couldn't run the washing machine off it, so I'd have to switch over and run the washing machine off a generator. But that's not very common anymore because most inverters have a lot higher ratings. You know, it's typical 5 kilowatts or more for single phase. And also they often have their own internal bypass so that when a generator is provided to them, they can take the generator input and synchronize their own output with it and provide power to the loads. I've also tagged at the bottom of that list something called a microgrid. Now, I've actually run a whole separate course on microgrids. Microgrids is where you've got multiple installations that share a common grid. So you might have a central system that's your grid forming system. And what we have here at the Smart Energy Lab is a 45 kilowatt power chain from Cellectronic, and it's made up of 6 7.5 kilowatt inverters, 2 per phase, and that creates a 50 hertz, 400 volt 3-phase grid to which all of the homes on the microgrid and all of the other equipment, my labs and testing labs, and also my studio, what I'm in at the moment, all connect to. But microgrids are more applicable where you've got multiple generation and storage in close proximity. So the design process is starting with component sizing and selection, finding out what your major components are going to be. Things like inverters, batteries, etc. You may have reasons for choosing particular brands. Often there is like some logical combinations where a certain battery type and a certain inverter type work well together. For instance, in this picture, and by the way, this is a fairly old picture, a beautiful looking install from Off Grid Energy, and this would have been done before 5139 was published because those HRC fuse switches are no longer permitted to be main battery isolators. So anyone who's going to dob me in for that this is an old picture, and they were perfectly okay. They work fine. They're just only IP20, and we've moved up the requirements to IP23 now for anything that's an isolator on a battery system. So yeah. Also, the other thing to consider is how do you monitor it? So metering and control and monitoring. So it's all very well to build a system, but if you can't keep an eye on how it's performing, how much is in the tank is how people often phrase it, you're going to be running blind. So it's very important that you've got a means of identifying how much storage is available and what energy sources are currently powering it. So, for instance, in this picture we can see Fronius. They're probably three-phase, looking at the fact there's 3 SP Pros there. So some Fronius Symos and some Selectronic SP Pros on the wall. Now, the SP Pros have an on-screen display, which is a simple bar graph, but it actually is pretty useful just to stand in front of that equipment and to be able to see a bar graph. I think it's got 7 steps in it, and it tells you how much capacity is in your battery. The on-screen display can also tell you what sources are charging your batteries. Are they renewable? Are they non-renewable? And also some alarms and warnings. So the other requirement is that the system has all of the safety features that you would expect in any electrical design, things like overcurrent protection, points of isolation and control. So all of that is part of the design process. Now, most installers who do off-grid systems will have their favourite products because off-grid is more complicated than on-grid generally, and you probably are familiar with particular products, but also off-grid is so much more critical than on-grid. I mean, if an off-grid system fails, you have no power. If an on-grid system fails, you've probably still got power from the grid. It's just not saving money. And so your quality of life doesn't change in an on-grid system if there's a problem, but an off-grid system, no power is pretty serious. I sometimes talk about something called the Maslow's hierarchy of needs. Now, if you're into psychology, you might know what that is, but I do a sort of energy hierarchy of needs. It's sort of the same concept as Maslow. And this is how I'd like to explain it. If I've got my little overhead thing here, let's have a look. I do this with a customer too to sort of explain why certain things are very critical in a design process. And where's my overhead? There. And where's me? And where's my overhead? Oh, sorry, I'm having a little troubles with my cameras. That's E. There we go. All right, so this is my little overhead. So let's draw a pyramid here. And we'll call at the bottom is the most important things. What are the most important things for living off-grid? Now, you might think I'm facetious here, but I'm going to say air. You need to breathe, right? You'll see where I'm going with this. You can only last a few minutes without air. Probably next on the list of most important things is water, okay? And I'm talking about water services, not just drinking water, but also flushing toilets, washing, etc. Those are pretty important. After water, I'd say comfort. Now, comfort is things like temperature control. Is it warm? Is it cold? Is there a fan blowing? These are nice things to have. On top of that is you probably get hungry from time to time and you'll need a way of storing food, particularly refrigerated food. So food's pretty important in that hierarchy of needs. Then you might also have a need for some friends. So we've got socialisation, things like you've got a nice home where people can be entertained, and we'll call the last one peace of mind. So this little hierarchy is from lowest to highest importance, and let's talk about off-grid. So we're going to have a bit of a problem with our off-grid system today, and the power goes off. So our peace of mind is not so peaceful at the moment. We're worried about having lost power. And we just, yesterday we invited some friends around for dinner, but we're going to have to cancel that because we've got no lights. So our socials have gone off. And now our fridge is starting to warm up, and it's day 2 without power, and now our food's starting to spoil. And what do you know? It's a hot summer here in Australia, and no cooling fans, no air conditioning. Our pressure pump that delivers water to our home. Now, you can see that life has suddenly got pretty bad just by turning off the power if you're off-grid. The good news is you can still breathe. So we're down to just breathing. And from from an installer's point of view, this is the reason that you have to take it really seriously when you design off-grid, because the customer is going to have no qualms about calling on Christmas Day and expecting you to come and fix things. And they tend to be a customer for life too. You're going to do upgrades, and you're probably going to have a few training sessions with them and help them explain and understand how their power system works. So yeah, off-grid is a much more serious game than on-grid. I should also say that to gain access to any of the rebates here in Australia, you need to be accredited for off-grid, and there's some excellent RTOs that provide off-grid training courses for electricians, so they can be accredited with SAA for standalone power systems. Okay, so where are we? Get my little slides back and put myself down the bottom there. Okay, so what's next? Well, you need to provide some information as part of design to the customer, and these are called performance estimates. Now, for an on-grid system, it's really it's still a requirement in the 5033 standard is to provide an estimate on the system's performance. But for off-grid, it actually is pretty critical, because you're going to say what the system's capable of and what it's not capable of. So I like to think of there's a few ways that you can size an off-grid system. And once again, I'll bring my little drawing up. Where are we? Here. So you can size a system. The simplest way is to a fixed capacity. So the system has a capacity of so many kilowatt hours of energy per day, energy storage, right? And there'll be a dollar value for that. And you might say, this is our 10 kilowatt hour a day system, this is our 20 kilowatt hour a day system, etc. So that's kind of the most simple, but it means that all of the responsibility for it being the right size falls on the customer's shoulders. And if this is the first off-grid system that the customer's ever had to live with, it's unlikely that they have any idea about what size system they need. I mean, a rough guide might be how much power do they currently use and looking at their power bill, but you've got to consider days of autonomy as well, which is how many days can you run when the weather's bad. Excuse me. So, for instance, if you've got a solar system and it's wintertime and there's like a week of rain, it's not just good enough to have 10 kilowatt hours of storage for your 10 kilowatt hour per day usage. It's got to cover all the days when there's no input as well. And that's called days of autonomy. The second system is a budget, right? So that means the customer says, I have, X number of dollars, and what can you give me for X number of dollars? That's a pretty terrifying position, actually, as an installer. It means you're probably going to be cutting a lot of corners to get it fit in their budget. I mean, unfortunately, there's lots of ads on television and social media for on-grid systems that cost so little. I mean, on a Friday afternoon, you might see one for $3,999 fully installed for a 5 kilowatt on-grid system. Even more ridiculous numbers than that. And so customers get this idea that solar is really cheap. But off-grid, the difference is you need storage, you need something that can run everything, not just run a few things on backup. And so they're much more expensive. And I'll tell you my tire kicking solution too, how to find out if the customer's serious or not pretty quickly in a minute. So the third option, and I'd say this is the right option because it's going to be based on what the customer needs, is to a customer's load requirement. I can't even spell. So what are their loads and what is their maximum demand? And we're going to design a system. And this here is what AS/NZS 4509 Part 1 is all about, is designing a system, Part 2, is all about. And that's what we're looking at today. Cool. By the way, feel free to ask me questions in the chat, and I'll respond to them if I see them. I'm just looking at the chat now. And if you just joined us, let me know where you're watching this from. I always like to get a sense of where my audience is coming from. I am focusing very much on kind of Australian and New Zealand standards, but these design principles apply anywhere. So you could just consider this best practice advice if you live anywhere else. So, where are we? You also need to come up with an electrical design. Considering things like what the maximum demand is and ratings of cables, possible locations for the system, all of this. And so that's another part of it. G'day, Wayne from Melton, sorry. And mechanical design, basically, where's it going to go and how are you going to build it? Is it going to be a roof-mounted system, a ground-mounted system, etc.? Step 5, costings and economic evaluation. Now, there's this kind of tension between what a customer needs and what their budget can achieve. Bit like the Rolling Stones song, you don't always get what you want, but you get what you need. That's why doing a design and based on a customer's load requirement and then being able to turn that into a costing is really important. So this is where my next step comes in, which is how to solve the problem of tire kickers. Now, I'm not being mean, but some people have no clue about the realities of building an off-grid system, and you can spend a lot of time talking them through their options and going through some design process and maybe doing some calculations. And when you cost it out and give them the number, they go, oh, I didn't think it was going to cost that much. And so you've just kind of like wasted a lot of your effort. Another approach is to give them a ballpark figure based on how much energy they need. And so I call this dollars per kilowatt hour. So let me draw this one up for you. So how do we work this out? So I call this a standalone power system build cost. So how much is it going to cost to build the system? All the components plus labour and installation. And the way I do it is come up with a figure for dollars per kilowatt hour per day of energy required. Now, it is a pretty rough approach, but like I say, this is to help sort out some tire kickers from people who are serious. Now, I use a number based on my experience for the type of systems that I would build, and I cost a standalone power system with quality components at around about $2,000 to $4,000 per kilowatt hour per day of system build price. Okay, so what does that mean? Well, if you speak to the customer and ask them, have you got a bill? Can you show me, how much you're using, and I'll calculate for you what the price will be. You can basically go, well, my bill is currently on my home showing that I use around about 20 kilowatt hours per day. Okay, and so therefore I multiply those two numbers, either 2,000 to 4,000, to give a total cost. So the total cost will be somewhere between 40K and 80K complete built. And if you throw those numbers out early in the discussion, you can save yourself a lot of pain because they might go, oh, I had no idea it was going to be that expensive. Now, there are ways of, and also they might say, well, how come you're giving me such a big range? Well, the range is actually to do with the days of autonomy. So, for instance, on the low end, at $2,000 per kilowatt hour per day for system build price, that would be with only 2 days of autonomy, only 2 days that you can run without having to turn on a backup generator. Whereas $4,000 per kilowatt hour per day would be for a system capable of more like 4 to 5 days of autonomy, which should get you through most weather cycles. So that's always a good thing. I just noticed one of my cameras turned off. Hang on. Hopefully that comes back on. There we go. It's come back on. So, sorry, little wobbly camera. Bumped you. So that's a way of kind of quickly getting to the meat of it. Is this customer serious? But I'll explain how you can help them with this figure, because this figure is totally proportional to that number there, the kilowatt hours per day. If you can help the customer become more efficient, choosing smart appliances that are more efficient, you can reduce that number and therefore reduce the bill price. So that's really important. Now, you also need to consider things like what are you competing with? The cost of connecting to the grid. I mean, sometimes you might spend a whole lot of time designing a system and it turns out they're going to cost, $80,000. And then they go, oh, we had a quote to connect the grid for $16,000. You go, well, it's your choice, mate. That sounds pretty good to me. So, it's worth pointing out that with a standalone power system, you are pre-purchasing all of your energy basically for the next 10 years. Now, it's typical warranty on a battery system. And so you're pre-purchasing all of your costs up front, whereas an on-grid system, you are basically paying it forever. So that initial expense for the connect is then not the total cost of ownership. G'day, Kagari Gaz from Fraser Island. Hey. Good. Hope the weather's all right up there. You've had a few tropical storms, I believe. It's been a bit rough this year. Been a bit rough down in Victoria too with fires, but so far so good. We're okay here, but people a bit north of us not so happy. So cost of grid connectivity is one to find out early on, just to see what you're competing with. Then lastly, expandability. Just consider that can the system grow with the customer's needs? Some systems, like, when I first started doing off-grid, it was all lead-acid battery times back then. And lead-acid batteries aren't expandable, right? Basically, you buy your lead-acid battery and you use it up and you recycle it. And if it's not big enough, well, that's pretty tough. It's not something you can just throw a few more batteries on and make it go bigger. So expandability is something to consider. But these days with modern lithium-ion batteries, it's a lot easier because often they're modular and you can add more storage capacity. But consider expandability. So it's something you should raise with the customer when you're discussing with them the design. They might be a young couple with no kids and they're probably used to living simply, but once kids come along, it gets a bit more complicated. They might want a washing machine and dryer and a whole bunch of other appliances and whatever, and suddenly power use is going up. So watch for that one. So the design process also includes producing documentation. Now, documentation is a mandatory requirement in all our standards for renewable energy, whether it's for PV arrays, for on-grid hybrid systems or off-grid systems. But for off-grid systems, the documentation is really important. Basically, it should provide information how to manage the system, how to maintain the system, and enough information for other professionals, electrical workers, to be able to work on that system even if they didn't build it in the first place. And so things like schematics, lists of products, a maintenance schedule, all of that is pretty important, along with the usual safety signage and safety information. And I'd also suggest that you consider having a training session. It's not really just I've built you a standalone power system and I'm walking away now. There's a bit to learn about operating it, and what's normal and what's abnormal operation, what to do in case of faults, etc. These things are pretty important. Now, I've talked quite a lot about the amount of energy required, but we also have to consider about the amount of power required. Now, those two things sound like the same thing to some people, but from a technical perspective, energy is power times time. So energy is work done, whereas power is instantaneous. And that's what an inverter has to deliver. An inverter has to deliver a certain amount of instantaneous power. And it's not as simple as just knowing what the power rating of an appliance is. You need to know if it's also got a surge demand. Now, this is a very real problem for off-grid, because often you'll have quite a lot of coincidental loads. That means things that come on at the same time, and they can basically overload your system. So it's pretty important that you consider what appliances are likely to be running at the same time. Now, here's a typical scenario. You've got a kitchen, and you get up in the morning, and what happens? Well, you forgot to put the dishwasher on last night, so you put it on. That means that it's drawing water, and so the pressure pump comes on, and that's a big surge. And the dishwasher then goes to heat that water, and there's no surge, but quite a reasonable power demand. Then you turn on the coffee machine, and so it ramps up. There's a bit of a surge. You might then put on the toaster, and there's another high-powered appliance. And before you know it, you've got yourself, 6, 7, 8 kilowatts of power being used in the kitchen, and the pressure pump might spike to many times its power rating. So pressure pumps, say a single phase one, might be rated at, say, 300 watts, but it might surge 5 to 7 times that on start. And so the inverter has to be able to deliver that. And that's what we call maximum demand. If you're used to doing the calculations in ASNZS 3000 for maximum demand after diversity, it really doesn't apply to systems that are delivered from an inverter, because there is no diversity factor with the inverter. It's got a hard limit in terms of its power rating, and you can't sort of use the same concept that you've got a little bit of headroom built into it. It'll have a hard limit in terms of the amount of power it can deliver. So coming up with a surge demand design, and also you need to consider what's known as real and apparent power. So now we're getting a bit technical. Some appliances have what we call poor power factor, and that means that the inverter has to deliver more power than is actually used. Now, it doesn't really sound right, does it? But what's known as reactive power is caused by the fact that the current and voltage can be slightly out of phase with each other, but that means that there's a certain amount of energy that's being returned in the circuit. That reactive power is being returned, but it still has to be produced. And it also causes losses in cables, etc. So calculating that as well is a bit more technical. Then we've got to understand not just the power rating of appliances, but how often are they used? And that's when a load sheet comes in. So this is probably too small for you to see on screen, and I call this homework. But really, for me, getting the customer to complete a load sheet is part of them qualifying as a customer for me. If they're not prepared to tell me what appliances they want to run in their off-grid system, you're working blind. You can sort of assume a few things, probably a fridge, probably lights, but who knows what else is going in there. And so having a simple load sheet, it's got a few columns in there, so you'll have a list of appliances, quantities of those appliances, like for instance, how many lights are there, the power rating of each of those appliances, their daily usage, and then you can calculate from that the watt-hour demand of each appliance. So multiplying quantity by power by time will give you watt-hours, and that can be summed up to give you a kilowatt-hour total. And so you can use this to size the amount of storage required to meet, for instance, their nighttime loads. So a load sheet, really important. It's also your opportunity to help the customer save money. Why do I say that? Well, it's pretty quickly you can identify who the bad boys are. What's causing your cost of building a system to be so high? It could be because of some of the appliances in your list. So what you're looking for is efficiency. And efficiency can be sometimes referred to as negawatts, the watts that you never needed. And choosing appliances that are efficient can be an upfront saving on day one, not just an ongoing saving, but it means you don't have to build such a big system. It doesn't have to deliver such high surge demands. It doesn't have to store so much energy because your appliances don't use much. And I like to give the sort of an example of a refrigerator. A refrigerator is probably the only appliance that you buy and never turn off. It's right. It's on 24/7 for the rest of its life. Sometimes it's retired, in air quotes, to the back shed where it becomes a beer fridge. So it lives a long life. Now, if you look at a fridge that's got a bit of age on it and it's probably not that efficient, you might have an old sort of fridge that has fairly poor compressor technology. It might be using, let's say, 3 kilowatt hours per day. And that old fridge, if you use my calculations for $2,000 to $3,000 per kilowatt hour per day of energy demand, that fridge is actually going to cost you $6,000 to $9,000 to build a system to run it. Yeah, right. $6,000 to $9,000 just to run your fridge, for the solar and battery capacity to run it. Whereas if you bought a brand new fridge with a 5-star or even better rating, and that fridge is only going to draw use 1 kilowatt hour per day, suddenly your build price is halved. Well, even so, you're in this case gone to a third. And so you're only going to spend $2,000 to $3,000 to build a system to run that fridge. So you're helping the customer save money by, ironically, choosing brand new appliances to replace their old inefficient appliances. So that's what a load sheet can be useful for. You can also identify some appliances that are just not practical for their budget. I did actually once have a customer who wanted 24/7 aircon because of their health conditions. And they had to keep their body with, I think it was the thyroid wasn't functioning properly, and they had to stay within a narrow temperature range for health reasons. And it was, where it would be heating sometimes and cooling at other times. So the energy demand for that system would be really high. And when I costed it, they said, well, we can't afford that. Well, I go, well, maybe you can't afford to live off grid with your health condition. I mean, it's a bit harsh, but you've got to be realistic about this, considering that some appliances are going to draw a lot of energy. But then again, not all customers are budget constrained, and sometimes you just go, well, go big or go home. I've had some really exciting systems. I think you probably must have seen on my channel. I built a 366 kilowatt hour battery system for a customer just to run his swimming pool. Yeah, off-grid swimming pool. Wow, that's an expensive swimming pool, but there you go. Where are we? So the other thing is to look for opportunities for energy efficiency by turning stuff off. It's called using your finger to save energy. And there's these invisible loads, what we call standby loads, things that you think are off, but are still consuming power. And one way to find out is if they're warm, warmer than the room, they're probably consuming power. Things like, stereos, TVs, plug packs, gaming equipment that goes into sleep mode but actually still on. And all of that adds up. Typically, a home will have about 10% of its power demand is just standby loads. So being able to work out what is what standby loads there are likely to be, and how to reduce that demand, and that can be just by switching it off at the wall. So training a customer to be more energy efficient by turning off standby loads. Now, I said that maximum demand is something that needs to be calculated, the number of coincidental loads that all come on at the same time. But sometimes you can solve this by explaining to the customer that they need to stagger some of those loads. For instance, don't put the clothes washing machine on at the same time as the dishwashing machine. because they're both going to be drawing water, running the pressure pump and heating water, and therefore you're putting a lot of maximum demand on at the same time. Or they might have an appliance that is a rarely used appliance, something like a... oh, the camera's gone off again. You know what? I think my camera's getting a bit hot, so you'll just have to look at my slides. It's probably a relief. Yes, so some appliances are just so big that you have to consider them as a rarely used, and therefore make sure that other loads aren't on at the same time. So that might be something like you've got an arc welder in the workshop, and when you strike it, it draws a lot of power. You might try and avoid using the arc welder when you're also using the washing machine and dishwasher. So putting that in a load sheet and getting the customer to sign off on that as the agreed design is a really good protection against the customer saying, well, this system doesn't work. Well, it does work, but it can't do everything. So you have to put some limits around what is achievable and what is not achievable, and therefore the customer has to make some choices about which appliances run at the same time. Now, if you're really into automation, you can actually use load shedders. Now, a load shedder is basically something that the electrician will install as part of the switchboard, and it'll have some contactors that control various non-essential loads. And the load shedder can turn those loads off when you reach a certain maximum demand. But that's a really good way of solving or automating that process. I mean, loads that aren't sort of critical would be things like water heating, pool pumps, maybe even an oven. Something that, well, actually, if you're baking a cake, it probably isn't a great thing to turn off the oven. But things that you can shed, i.e. turn off automatically when you're approaching your maximum power of your system. And that's a good way of kind of set and forget. G'day, I just saw a hi from Quaho Solar, so if I said that properly. And g'day, David. Good to see you. And, from Somalia. Wow. What time of day is it in Somalia at the moment? Is it nighttime? You're on the other side of the planet to me. That's amazing. Great to have such a wide audience. Yeah, so welcome all those who just joined. So we're talking about managing maximum demand by using things like load shedders, or even just training the customer on what's feasible and what's not. So a demand assessment is also has to meet what your production of your solar system's capable of. And so you need to consider, for instance, the sum of all of those demands, all of the power demands times their usage, and that will give you a daily usage time in hours. So, and multiply that by power, and that'll give you a energy demand for the day. So we'll look at some of those formulas in a minute. None of it's rocket science. You could do it on a pocket calculator. You also need to consider if there are any DC loads. Now, DC loads actually have a little bit of an advantage here, which is they don't increase the maximum demand on your AC inverter, because your AC inverter is going to supply your AC loads. But if you've got things like a DC pressure pump, a DC lighting, there are even DC fans. In fact, DC fans are very nice. They tend to have a much nicer control system and more efficient. So if you've got some DC loads, they don't add to your maximum demand on your AC bus, but they do still consume energy. So they do still affect the amount of energy that your system needs to provide from a battery or from storage, basically. So why would you have DC loads? It does give you a level of redundancy too. Now, this is not very common anymore, but certainly when I first went off grid, I was always a bit concerned about if my inverter failed, would I have no lights? And so I had DC lighting in my home. In fact, I still have DC lighting in my new home. And I used to have a DC water pump, because those two things are pretty critical, having water and having lighting, and having maybe some cooling like a fan as well. So if you don't put all of your appliances into the AC bucket of energy, it gives you a bit more redundancy, but also helps with maximum demand. Inverter efficiency. Okay, so this is really just help you understand how efficiency is affected by load. Now, you might think, well, my inverter is 94% efficient, so it's really, really good. But if you look at the efficiency curves, it'll be 94% efficient somewhere up in the higher power levels. So power on this curve is across the bottom, because at low loads, there is a certain amount of self-consumption, and that self-consumption is always there. It's basically the electronics within the inverter, some circulating currents within the transformer, etc. And that means that inverters will be effectively consuming power even when they're not doing much. And you need to consider that as part of your energy consumption design for your system. So what else? I just saw another person say hello. Oh, it's David. G'day, David from DPA Solar. David's just pointing out that they have an easy off-grid calculator on their support tab. Okay. So DPA Solar, or DPA Energy, sorry, based in Melbourne. David, I know David. He's worked for them for a very long time, designed systems like this for off-grid. Anyway, back to my slides. I think I've already mentioned this is the coincidental demands, and just an example here that you might actually have three things that always come on together because as soon as you turn on your washing machine, your pressure pump comes on and it draws water. It might be drawing hot water, which might mean that your heat pump kicks in because it's got to maintain a minimum temperature and it's just dropped below 60 degrees, and so it's turning on its boost, and all of that adds up to a coincidental demand. So just beware of those kind of scenarios in a system. Surge demand, now we are getting rather technical here. Appliances that are purely resistive, that means they don't have a motor, for instance. A spinning motor is going to have a startup surge, but something like a resistive heater, and there's a picture of a heater at the top of this picture here, it's not going to have any surge demand. It's just going to have continuous power rating. So a heater is, in a way, a bit friendlier to inverters. It doesn't have a power factor, or it has a power factor of 1, I should say, unity power factor. But then things which have motors and also some types of lighting, which have reactive power as well, they can basically cause a bit more problems, both in terms of your continuous power demand, but also your surge demand. So a motor, particularly a synchronous motor, when it first turns on, is effectively a short circuit until it starts to spin and create a magnetic field, which reduces the inrush current. And so the moment you turn that motor on, it could be drawing, up to 7 times as much. So induction motors, really high surge rating, and that has to be delivered by the inverter. Now, there are ways of reducing that surge. One of the best ways for motors is a variable speed drive, which is basically an electronics control system, sometimes called soft start or inverter control. A lot of air conditioners these days have the word inverter on the front. What they're doing is they're taking AC power, converting it to DC, and then energizing it as AC, but in a variable phase angle to give a variable speed. And generally, they'll output at 3-phase too. So a variable speed drive, or VSD for short, is a great way of getting rid of that surge demand. So I've got a variable speed drive on my pressure pump. I've got an AC pressure pump here. I think it's about a 2 kilowatt unit. Now, a 2 kilowatt pressure pump is actually a pretty big pump for a home. And considering that if it had a 7 times surge factor, that's 14 kilowatts when it turns on. But because it's controlled by a variable speed drive, it only ramps up proportional to the amount of water that you need. And so you can actually hear it going as taps go on and off. And there's no sudden inrush. So that pump actually helps reduce the system size I need to run it. So once again, it's sometimes choosing appliances can save money. So yeah, VSDs for pumps, great idea. DC pressure pumps, they're really quite small generally, but they're ideal for smaller installations, like, maybe just a cabin, and they don't need an inverter to run. They are rather noisy because they have a very loud reciprocating motor inside them, or pump, I should say. But apart from the noise factor, they don't use a lot of power, and they can deliver a reasonable amount of water, maybe running one shower and one tap or something like that. So yeah, you can actually just get DC pressure pumps instead of running AC ones. You also need to consider seasonal variation. It's all very well to calculate the customer's energy consumption, but you need to consider how that varies with the season. They might use very little in summer because they're outdoors most of the time and they're not using any thermal loads, they're not heating or electrically heating. But come wintertime, they're indoors more, there's more indoor activity, watching television, more lights are on, and their power demand goes up. So being able to calculate at least a summer and winter or a wet season and dry season load assessment, and then choose the one that has the worst relationship to their resource. Now, what's known as the load resource ratio. For instance, in wintertime, you might be using more power, but actually there's less solar resource available, and that means that that's the worst time, in a way, to try and meet the energy demand. So you need to size the solar system for the winter cycle. Whereas in the summertime, that same solar system might have a lot of excess capability, which you don't need. But in a way, that's a good thing because you can consider that discretionary energy. You can choose to run the aircon because you've got plenty of power in summer. So calculating seasonal variation. Even things like how some appliances, their efficiency changes with the season too. So things like a refrigerator in a very hot room is going to use more power than a refrigerator in a cool room. So that can be a factor as well, but not a big one. How do you assess the resource? Now, when I'm talking about the resource, the renewable energy resource, for a solar system, being able to do a site analysis. Now, what you're looking at there is a very simple tool, but quite effective. It's called a Solar Pathfinder, and basically it's a hemispherical see-through dome that reflects the sky and all around that you can look down into. And there's a chart inside there that shows you by time of day and by month of the year when the sky is visible. And i.e., if it's sunny, the sun can shine through. And if you can see in this picture, around the edges, you can see some trees and a building, and those would be obstructing the path of the sun at different times of the year. So the top of this graph is, or top of this chart is for winter. June is at the very top, and then the lines towards the middle is summer. And so you can see there's more hours of the day that sun's available in summer than there is in winter. So this gives you a realistic view of what your solar resource is. A tool like this actually is quite sophisticated. It looks very simple, but you can actually use a calculator to work out for each half-hour interval of the day how much energy is available as a proportion and a percentage. I won't go into that now. There are other tools, things like the Sunmetric SunEye, which is like a PDA device that does a similar job, or even just some apps, some simple apps. One of my favorites is called Sunseeker. See if I can find it on my phone for you. There we go. Sunseeker. I turn my overhead camera on because that seems to be still working. There we go. So this app here uses the smarts of your phone, and it can calculate the altitude of the sun for different times of the year. And you can see right now the yellow line is showing the path of the sun. The concentric circles represent the degrees of altitude of the sun. So, and it's using the GPS in my phone to calculate all those angles. But you can also put it in 3D mode. Now, this is not going to work inside, but if I put in 3D mode, it actually uses the camera I don't know if you can see, you can't really see very well, but it uses the camera to show you where the sun will be. So you can just wave this around roughly in the northern direction if you're in the southern hemisphere at the site where you plan to put the solar, and you can pretty quickly see when the sun is going to be obstructed and when it's not obstructed. So using the Solar Pathfinder, what's it called now? I've forgotten the name of this app. Sunseeker. It's a paid app. I think it costs, a couple of dollars or something. It's not very expensive. But yeah, it's quite a useful little tool to do a quick site assessment. All right. When it comes to wind and hydro, it's kind of out of the scope of my quick chat today, which, by the way, I just realised I'm running out of time. Wind being probably the most difficult because it's so site-specific, and if you want to be good at it, you really probably need to put up a test turbine or even just a test anemometer to measure the wind, and you probably need to do it for a whole year to get a good analysis. Though there are sites that have what they call wind roses that's showing you direction and strength of wind over different seasons, and they can be used to do an assessment of the site. But really, to cut to the chase, wind is very, very site-specific these days and generally not very cost-competitive with solar. So if you do have a suitable solar site, you'll be much better off just using solar as your primary resource. Wind could be an adjunct to that, and particularly if you live in somewhere very in the sort of southern states, maybe down in Tasmania, where your solar resource is somewhat less, but you've got some great wind resources, particularly on the west coast. In fact, the west coast of Tasmania has an awesome wind resource. Now I'm just going to turn my camera back on. I think it keeps turning off. It must be getting a bit hot. But I thought I'd just run through some of the basics of understanding a standalone power system. And let me bring back myself. There we go. So very high level discussion here on designing. This is actually an introduction to a full course. I'm just giving you a few of the intro slides here to give you an idea of what's involved. But we get down to the nuts and bolts of designing a standalone power system, right? Doing all the calculations to size the PV, to size the battery system, to size the inverter, to meet an energy demand. And that's to be compliant with the Design Standard 4509 Part 2, 2010. So that's all for today. Hope you enjoyed another Toolbox Tech Talk. But otherwise, I'll check out and I'll see you next week. See ya.